In the previous set of videos, we went through double and triple integrals as well as some examples associated with them. Now, today we are going to address coordinate transformations. These coordinate transformations are important in solving or in evaluating some complex integrals. For example, in this case, in this endeavor, our attention is focused to these three coordinate transformations in particular. First, polar coordinates, which is used in R2 in two-dimensional space. When the domain of integration is a circle, this transformation is always useful, because once your domain of integration is a circle, it is extremely hard to find limits. Even though you can find limits, it is extremely hard to evaluate the integral once you are restricted to rectangular coordinate system. Therefore, in that event we use polar coordinates. Remember, the domain of integration has some circular shape. It can be a circle, or it can be some kind of a sector, portion of a circle, or something like that. Then polar coordinates are useful. The second one is cylindrical polar coordinates. Cylindrical polar coordinates are used when you are in R3 and the domain of integration is something like a cylinder or a portion of a cylinder. The third, spherical polar coordinates. Spherical polar coordinates are used when you are in R3, when the domain of integration is a subset of R3, as well as it is a sphere or it is a portion of a sphere. For example, hemisphere or some portion of a sphere, then spherical polar coordinates are very useful. Without spherical polar coordinates, it is extremely hard to evaluate that integral. Okay. Now, we will move to the first one, part A, polar coordinates in R2. Now, if you consider, now we are familiar with rectangular coordinate system. So, this is the rectangular coordinate system. It looks like the atlas, like these lines can be understood as longitudes and latitudes. So, it is like an atlas. On the other hand, if you consider a globe, if you look at from the top, the north pole looks like this. Now, this is the polar coordinate system because of that, because this looks like the north pole. The longitudes and latitudes look like this. This is the north pole. Therefore, this system is called polar coordinates. Remember, here, if you move along this line, always if you move horizontally, y is constant. If you move vertically, x is constant. In that case, if you move along this circle, rho is constant. Rho is the distance from the origin to any point on the plane. Here, for example, if this is 1, then rho is 1 along, on this circle. Here, rho is 2 on this circle. Right. On the other hand, theta is the angle measured from the positive direction of x-axis in anticlockwise direction, like we usually measure angles in trigonometry. So, this is 0 on this line, on this portion of the line, theta is 0. Here theta is 5/6 or 30 degrees. Here it is 5/3 or 60 degrees. Here it is 90 or 5/2 radians, like that. Now, if you move further, like if you take the polar coordinate system, you can see this distance is rho. If you take any point here, the distance from the origin to this point is rho. The angle the anticlockwise angle from the positive direction of x is theta. Right? You can see if you want to increase rho, right? Rho is the distance from the origin to any point on the plane. So if you want to increase that distance, you have to move further away like this. You have to move further away. So if this is rho, the direction which increases rho and the unit vector along this direction is denoted as rho hat. Similarly, this is theta. So without changing the value of rho, or on the other hand, without changing the distance from the origin to this point, if you want to increase theta, you have to move along this direction. So that's, if you take the unit vector along that direction, that's called theta hat, because that's how, without changing rho, you increase theta. Here, without changing theta, you increase rho. Again, if you come back to, if you come back to the rectangular coordinate system, like if you move this way, without changing y, you change x. That's the direction, that's the vector I. On the other hand, if you, without changing x, if you want to change y, then you have to move along this direction. That's a vector j. This vector I, this vector j. You can see they are mutually perpendicular. Here also they are mutually perpendicular. Rho comes first. Therefore, we call it as rho theta coordinates. Like xy coordinates, rho comes first, because you can see the orientation. From rho hat to theta hat, the angle is 90, and you measure in anti-clockwise direction. Therefore, rho comes first, theta follows it. So it's rho theta coordinates. Now, what's the infinitesimal element, or the area of the infinitesimal element in this coordinate system? Now we will see. You take any point on the plane, the distance from the origin to this point is rho. That means the first coordinate is rho. Now, if the angle from the x-axis to this line is theta, and it is rho theta, the coordinate here is rho theta. Now, if you increase rho infinitesimally by delta rho, now this length is delta rho. Similarly, you increase this angle by an infinitesimal amount. If this is theta, that infinitesimal amount is delta theta. So this angle is delta theta. Now this distance is rho. Therefore, the arc length, this arc length is radius times the angle. That means rho times delta theta. So this is rho times delta theta. This is delta rho. As you can see here, this is delta rho. Now, this is not a rectangle, but as delta theta, if these two quantities go to 0, this becomes smaller and smaller, and you can see that it has a shape of a rectangle. Therefore, under this condition, the area of the infinitesimal element becomes, when they go to 0, we replace them by d rho and d theta. Therefore, the area is rho d rho d theta. Rho d theta times d rho. So this is the product. So that's the area of the infinitesimal element. Now let's do a very simple example. Go through a very simple example. Let's find the area of a circle with radius r. We know what it is. It is phi r squared. The radius is r. Now if you use double integral and the polar coordinate system, here you take this as rho, the distance, you give a little increment, that's delta rho. This angle is theta. give a little increment to that as well, that is delta theta. We know that the infinitesimal area of the infinitesimal element is rho d rho d theta. As I explained earlier, that is the infinitesimal area of that element. Now, you can see that when you move inside this circle, the maximum distance you can achieve is r, minimum is 0. Therefore, rho varies from 0 to r. At the same time, theta, right, theta goes from 0 to 2 phi. Now, this is the infinitesimal area. You integrate it in this coordinate system. The rho the first variable rho, and this integration, this integral sign associates with, as we saw in the previous videos, with this one. So, the limits of rho from 0 to r, limits of theta from 0 to 2 phi. So, first you focus to this one. Variable of integration is rho. Therefore, rho squared over 2 is the integral. Then you substitute limits, you assign limits, then you keep the other parts intact. Now, when you plug in limits, you get r squared over 2 minus 0, so I ignored it. Now, this is what you have as your integrand. Theta is the variable of integration. Now, this is a constant, so r squared over 2 times theta is the answer. Limits are from 0 to 2 phi. Now, you plug in limits, this is what you get. Then these two, there are couple of 2's, they go away, leaving this as the answer. And we exactly know what the answer is. The answer is phi r squared, and that is what we got. So, we need to go through similar examples later. We will do them in the next video. Okay, thank you.